So for today, the first example here is another one where we can totally use method of undetermined coefficients if we had wanted to. You've got the side with all the dependent variables, has all constant coefficients. So this is somebody that we would have no problem whatsoever finding our homogeneous solution. Method of undetermined coefficients says, hey, as long as we have an e, yep, we've got an e function over here, we could totally use it. You could use variation of parameters on this method, except I didn't give you the formula for third order. So for us, for our class, variation of parameters wouldn't work only because we don't have the formula for third order. So what we're going to use instead of all of those other options is we're actually going to use Laplace transforms again. So the new thing on this example from last time is it's third order. Okay. Now, is there any difference than before? Nope. First step, you still have to go ahead and take the Laplace transform of all sides. So step 1. Take Laplace transform of both sides. So we'll have the Laplace transform of the third derivative. We'll have the Laplace transform of the second derivative. You could pull your coefficients out front always, so we'll have the Laplace transform of the first derivative times 3. And if we pull the coefficient out for the 5, this would just be the Laplace transform of y. And then we'll have the Laplace transform of 16e to the negative t, and personal preference, whether you pull that 16 out or not. Okay. So next thing we'd want to do is we'd want to go ahead and figure out what the Laplace transforms are of each of those guys. And I'll go ahead and do that over here to the side. Oh, that did not do what I wanted it to do. All right. So if we look at the Laplace transform of y, well, this is just going to be called capital Y. If we look at the Laplace transform of the first derivative, this is where we're going to use this rule. And let me scroll up so it's at the very top. Okay? So we're going to have s times capital Y, and then minus our first initial condition. But our first initial condition is 0, so this guy is just going to be s times capital Y. Now, if we look at the second derivative of y, if we look at his Laplace transform, and let me scooch this up so the formula is again at the very top of the screen there, this is going to be s squared times capital Y minus s times, well, it's still that first initial condition, which we know is 0, so this term will go away. And then minus our second initial condition, and our second initial condition is 2. So plug that all in, and we have s squared times capital Y, pretend that was a capital Y, minus 2. And then the last one we need is our Laplace transform of our third derivative. So this guy starts off with an s cubed times capital Y. Then we'll have s squared times our first initial condition, and we know our first initial condition is 0. So that term will go away. We then have minus s times the next initial condition. Our second initial condition we know is 2. And lastly, we subtract our last initial condition. And at this point, we'll just plug into that formula. So this guy is, what is that, s cubed capital Y. This term goes away because y of 0 is 0. Next, we have negative s. And the second initial condition was 2, so negative 2s. And lastly, we had negative 4, but we're subtracting it, so this will be plus 4. I would definitely recommend always doing those guys over to the side somewhere, or if you prefer, just write it under right here, but just to make sure you get those formulas correct. Now, putting this all together, that Laplace transform of the third derivative was our s cubed capital Y minus 2s plus 4. The Laplace transform of the second derivative, reading off from the side over there, is s squared times capital Y minus 2. The Laplace transform of the first derivative was just s times capital Y. And the Laplace transform of y, we just called it capital Y. And that's it for the left-hand side. We still have to simplify it, but that's taking the Laplace transform. Now, For the other side, the right-hand side, we've got that 16 out front, and we've got to use the rule for e raised to some power. So anybody remember the rule here for the e raised to some power? It's a fraction. Anybody remember what goes on the bottom of that fraction specifically? So the formula for e raised to the at is 1 over s minus a. So the 16 will multiply to get on the top to get 1 times 16 or 16. And then we have s minus a on the bottom. Well, in our case, our a is -1. So this will turn into s plus 1. Okay. So next stage that we want to do, after we take the Laplace transform, technically speaking, we can leave it just like this. But the next thing that we want to do is we want to solve for that capital Y. So step 2, solve for capital Y. Okay. So this is where you look to find your capital Y. So we've got a capital Y there, we've got one there, we've got one there, we've got one there. Notice you have one of these capital Y's, these Laplace transforms as your solution, one from each of the terms where there was a Y previously. So if we had order 4, you'd have 5 of those Y's. We have order 3, so we have 4 of them to worry about. So what we want to do is we want to pull them out and look at the factor, or look at all 4 of those terms. Okay? We'll go ahead and factor out the capital Y. So I'm doing 2 steps here at once. And from the first position, this would be an s cubed. From the second term that has a Y in it, we have an s squared. From the third term, we have an s, but don't forget the 3 here, so that's really 3s. And the last one down here, that looks like an s, but actually it was trying to be a 5. So this is -5. And notice, just like what we saw last time, if you have constant coefficients, the thing being multiplied by your y term looks like the characteristic equation of the associated homogeneous guy, except it uses s's. Then we look at everything that we didn't use with y, so the unhighlighted parts, and there's 1, 2, 3 of them. Okay? So we've got -2s, and when you add that 4 and that -2 together, you'll get +2. This means when we go ahead and solve for our capital Y, notice what happens. We can move the -2s and the +2 to the other side. So that would give us, and I'm on purpose going to move it over here, +2s minus 2, and then plus the 16 over s plus 1. Now, that would be the first step. Here's the second step. After we move this over, then we would divide, and instead of putting all of this over that, I'm going to write this part, this s cubed factor, as 1 over. In other words, I'm going to write its reciprocal. So here we've got s cubed plus s squared plus 3s minus 5. Now, no lies, that is not a nice expression. It is, however, correct that that is what the Laplace transform of the solution equals. You don't want to necessarily deal with it, but that's what it equals. So the next thing that we want to do is we actually want to find the inverse Laplace transform of this one, and I'm going to break this step into 2 parts. So step 3a, rewrite whatever your Laplace transform of your solution is in a standard form. In other words, put it in a format where we're actually going to be able to take its inverse Laplace transform easily. So this is where we do all of our algebra manipulation. This is definitely the step that is the most work of everything we're going to do today. Okay. So for this particular guy, what do we want to do? We want to get this into a single fraction. So there's a couple of different things that we can do. And what I would recommend is go ahead and write this part as its own little fraction first, and then go ahead and multiply them together. Okay? So I'm going to jump some of the algebra steps here only because of time. So the first thing is actually adding these guys together. So we have 1 over s cubed plus s squared plus 3s minus 5. Now I'm going to claim that the stuff inside of the parentheses, if you make common denominators and multiply it all out, should be 2s squared plus 14. And that would still be over the s plus 1. Okay. So then when we multiply through, that should be the new numerator, so 2s squared plus 14. And on the denominator, we have s plus 1 times something. And the times something is this guy. Now, that guy, anytime you have stuff in your denominator, there are two things that you look for, okay, two main things. You look to see if it factors, or you look to see if you can complete the square on it. Now, if you need to complete the square on somebody, you have to have your highest term to be an even power. Okay? So for example, if that had been s to the 4th, technically we could have completed the square on it. We're not going to have that in our class, or at least I don't plan to have that in our class unless something snuck through me looking at it in terms of web work where there's randomly generated things. Okay? So if we look for completing the square, you have to have your highest exponent on the s in the denominator to be even. In our case, we have s cubed, which is not even. So the thought is you might not be able to do completing the square, so you check to see will factoring work. And so what I did before we started class today is I looked and I said, hey, you know what, let me see if there are any factors that might work here. And notice at the end of this polynomial, this s cubed polynomial, there's a minus 5. Well, that minus 5 tells you that the only factors that are nice sort of normal factors that you would prefer to deal with would be things like s plus or minus 1, s plus or minus 5. So I tested them out, and one of them that worked was s minus 1. So instead of going through all of that testing, I'm just going to give you, when you factor out s minus 1, this expression right here turns into s minus 1 times something, and the something it turns into is s squared plus 2s plus 5. Now, in this situation, you then say, all right, well, I've got this s squared, this quadratic factor, and that quadratic factor now is somebody that you can say, hey, I would like to factor it a little bit further. Well, if you look at trying to factor it, it doesn't factor nicely. So if you tried to run it through the quadratic equation to see if you could find a root, in other words, to see if you could find a factor you didn't think of, like, I don't know, some funky factor like a 17 over 8 that you might not naturally think of. What you'll find is this guy doesn't factor unless you start using imaginary numbers. Don't use imaginary numbers. That right there is the indicator that this thing is going to be a completing the square term. Okay. So over to the side, I'm going to do something sneaky, specifically completing the square. So complete square, specifically on s squared plus 2s plus 5. And that is because this thing didn't factor. So we have the s squared plus 2s plus something plus 5. Anybody recall what we should put inside here? What should we add inside of those parentheses? Anybody got a guess? Yep, it'd be a plus 1. And remember, with completing the square, what do? You look at the coefficient on the s. You have it, so half of 2 is 1. You square it. 1 squared is still 1. And then whatever you added right here, and I on purpose color-coded it for you guys, you want to make sure you subtract that same exact thing from the constant at the end. And at this point, the stuff inside the parentheses is going to be something squared. Anybody grab what that something squared is? Hint, it's going to start with an S. It would be s plus 1. Perfect. Okay. Now, at any point in time, starting from now to most of the end of the problem, so not totally at the end of the problem, but close thereof, we can replace this expression of the s squared plus 2s plus 5 with our completing the square format, the s plus 1 squared plus 4. Personal preference if you want to do it now or later on. Honestly, it's a 50-50 shot. It's a coin toss whether I would plug it in right now or whether I would wait a little bit. So for right now, I'm just going to keep it to the side and we'll come back to it. What we're actually going to need to do here is we've got two terms that are factored and then one that doesn't factor that we'll use this completing the square format on it later, is we're going to actually use partial fractions here. So this is one of the rare times, okay, in practice it's actually not that rare, but this is one of the times where we're actually going to need both partial fractions and we're going to need completing the square. So just labeling what we did here. So you've got s plus 1 as a denominator, you've got s minus 1 as a denominator, and then you've got the s squared plus 2s plus 5 as a denominator. And s plus 1, s minus 1 are totally common denominators that we have seen in both our class frequently as well as in Calc 2 frequently. But the s squared plus 2s plus 5 is something that they skip in the Calc 2 course taught at our school. Why? I don't know. So does anybody have a guess on what the numerator or the top of that last fraction should be? Yes, perfect. So, well, change the x to an s and it's perfect. So here, c times s plus d. Notice that is the exact same format that you would have had if you had the standard quadratic term that they do teach in our Calc 1, which it would have been the s squared plus a constant. So like s squared plus 5 if you didn't have that 2s term. Turns out, if you have a quadratic, you can have any quadratic on the bottom of your partial fractions fraction if it doesn't factor. So the key thing there is doesn't factor. So anything that's an s squared plus some constant automatically doesn't factor, or I should rephrase, only factors with i's, with imaginary numbers. Same deal with this guy. This is one of the cases where we have that middle s term, but it still doesn't factor if you don't use imaginary numbers. So format-wise is that same guy. It's the general polynomial that's 1 degree less than whatever your non-factorable, non-reducible denominator actually is. Now, at this point, the algebra is going to get intense, so we're just going to highlight what you do, in part for time, and in part so you don't get bogged down in the details. So here, you'd set these two fractions equal to each other, and we'll solve for a, b, c, and d. Okay, so I know it's not all in one line, so pretend. What would we normally do? We'd multiply by our common denominator, so that would be this guy right here. If we multiply each of these three fractions by the common denominator, the fraction with the a in it originally would turn out to be a times s minus 1 times that quadratic guy, so s squared plus 2s plus 5. The middle fraction with the b in it would turn out to be b times s plus 1 times s squared plus 2s plus 5. I'm definitely regretting using 5s right now. And your last fraction will turn into its numerator, the c and the d's, and here we'll multiply by s plus 1, s minus 1. And all of this would be equal to the original numerator, the 2s squared plus 14. Yes, I know, it's a mess. Okay? Well, it's not really. It's just lots of bits and pieces. Okay? So if we went through and we did this, this is where you go and you'd plug in for the various guys. So something that would be common to use is maybe you say s equals 1. So if s equals 1, this would be 2. 14, this would be 16. S equals 1, the term with the a disappears. The terms with the c and the d would also disappear. So we're only going to be finding b. So we would have b times 2 times, oh my. So this is 1 plus 2, so that's 3 plus 5, so that would be 8. So anybody have a guess on what B would equal? What do you guys think? What would B equal? Yep, it would totally equal 1. Why? Because our 2 times 8 over here is 16, so when you divide, you'll just get a 1. No worries. Now, for the next one, the next smart S value to pick would be S equals -1. So here you had S squared, so the same 16. And when we look at our other side with our A, B, C, and D's, all the terms with S plus 1 would disappear. The second term would disappear, and that last term would also disappear. So we will be solving for A now. Well, when we plug in, we will have A. Then we'll get -2. Now the one that actually takes a little bit of work. S squared would be +1. 2S would be -1. So +1 minus 2 would be -1 plus 5. What is that, 4? So assuming we did all that arithmetic in our heads correctly, when you then solve for A, what would it be? Yep, perfect. So this would be -2. Now, S equals 1 or -1 are your two obvious choices for making everything look beautiful. Anybody spot what the next X value should be? Technically, you could pick any number you want as long as it's not 1 or -1, but there is a smart next X value to S value to pick, excuse me. Yep, definitely 0. So 0 being the smart S value to pick totally comes from the fact that right here, if you pick S equals 0, that will cancel out your C. Okay? Now, it will not cancel out your A or your B from the equation, but we've already solved for A and B, so you can plug it in. Now what you would have here with S equals 0, we get 14 on the left side. On the right side, we'll have A. A was -2. Then plug in 0 to S minus 1, we'll get -1. Plug 0 into S squared plus 2S plus 5, we'll get back 5. Then we'll do the same thing in the term with a B. B is 1. S plus 1 is still 1. And S squared plus 2S plus 5 is simply 5. Then we have D. Then when we plug 1 in for S, we'll have S plus 1 or 1. 1 in for S and S minus 1 would be -1. Now that one takes a little bit more work to clean up, but notice we'll be able to do it just fine. So this here is, what is that? That looks like 10. That looks like 5. Well, 10 and 5 is 15. If we subtract 15 from both sides, we'll have -1 equals -B, not B, D. So D here would equal 1. Awesome. So far it matches what the actual answer is. So we're doing good with our algebra. Now, last S value, totally personal preference. The only conditions here is you cannot pick 0 plus or minus 1. So anybody have an S value that you guys would want to pick? Please don't pick something like 10. Anybody have something they want us to use? Sure, that's a good choice. So say you pick S equals 2. So if we have S equals 2, we'll have 2 squared times 2, so that's 8. 8 and 14 is 22. Now, nothing is going to cancel, so we're going to get all of our A through D's, but we already know A, B, and D, so we're just going to solve for the unknown C. Let's plug it in. A, we said, is -2. S minus 1 is going to be 1. This expression here of the S squared will be 4, plus 2S will still be 4, so we're at 8. 8 plus 5 is 13. Then we have the term with a B, so B is 1. S plus 1 is 3. And we already found that the polynomial there, the quadratic, would reduce to 13 when S equals 2. Then we have the term with the C plus D. Some people like to actually split this and have it be, cover up the D, C times S plus 1 times S minus 1, and then fourth term, D times S plus 1 times S minus 1. Flip a coin, it doesn't matter which one works. Half the time I'll do one, half the time I'll do other. If this was a Cap 2 class, I'd probably split it into 2 terms So there's one with only C and one with only D. And this one I didn't bother, in part because I was about to run out of space at the side here. Okay. So if we plug in S equals 2, we'll have 2C plus D. Then we'll have S plus 1, so that's 3. S minus 1, that's 1. And I totally meant to not write a D, but the number 1, which is what D equals. And again, this is going to take a little bit of arithmetic, but we can totally do it. So we've got 22 right here. 2 times 13 is negative 26. 3 times 13, I definitely should have just added those together. Oh well. This is what, 39? These two will add together to be positive 13. And on the end here, we've got 3 times 2c, so that's 6c plus 3. So this tells us we have 13 plus 6, that's 16. If we subtract 16 from both sides, we should get back a 6 equals 6c, which tells us c equals 1. And that was exactly what we should have gotten. Now, what does this tell us? That was a lot of algebra to get to the following. This tells us that our Laplace transform of our solution is A over, where's A? A is negative 2, so negative 2 over S plus 1. Then we have B, B is 1 over S minus 1. Then we have C, where's C? C is 1, D is 1, so S plus 1. And on the bottom, here's where I'm going to go ahead and pull in the completing the square version of that denominator and replace this with S plus 1 quantity squared plus 4. Okay? So that's just plugging in the stuff we got from the partial fractions and going ahead and grabbing the stuff we did previously with completing the square. Now, at this stage, pull this back up so it's easier to see for you guys. That should be, roughly speaking, the right size. At this stage, we're ready to finish off. So this is like step 3, step 4. This would be step 4. Or step 3b, as we called it before. This is where we actually take the inverse Laplace transform, specifically of the expression we just found. So this tells us that our solution is little y, is the inverse Laplace transform of the expression we just found, so negative 2 over S plus 1. And while I'm writing this, start thinking about what you think that answer might be. The next fraction is 1 over S minus 1, and the last fraction is S plus 1 over S plus 1 squared plus 4. So, once we take the inverse Laplace transform, anybody have a guess what that first fraction is going to turn into? I guess I'll make notes here for us. So what type of function do you think that guy's going to turn into? So these two guys right here, both of them can totally be what? Both of them are e's. So we have e to the at. And the only thing that you need to grab is you need to figure out what the a was in that first one. The a was going to be negative 1. Anybody spot what the a would be for the second one? Ooh, the a for the second one is not going to be negative 1. What would be the a here? Yep, it would be positive 1. And then when we look at that last fraction, what function do you think that last fraction would turn into? Or what type of function, if you will? And while you guys are thinking and or typing, let me write what you said for the first two fractions down. The first one would be negative 2 e to the negative t, and the second one would be just e to the t. So this last one here would totally be a trig function, specifically a cosine, and it would be a format of, whoops, I meant that to be color-coded as scratch work. It would be an e to the at cosine of kt, where your a is that negative 1, and your k here is 2. So it is exactly what you typed in, which is e to the negative t cosine of 2t. Put in the formula there for everybody else. And that's it. That's the final answer. Note, these guys can get really, really snarly really fast, and it's not the first step where you take the Laplace transform. It's not the second step where you solve for the Laplace transform. It's not the last part of the third step where you actually take the inverse Laplace transform. The part where these things can get snarly really easy and really fast is right back here, where we were doing all of the algebra to rewrite the standard form that you'll get your Laplace transform in, this capital Y, and get it into a format that is actually something where you can take that inverse Laplace transform. Okay? Questions make sense? Kind of okay with that question. At least could follow it when somebody else did it. So yes, that is actually a perfect question. So what I've got prepped up for us today is I actually have a number of questions. But the last one that I think we're going to get to today is going to talk about exactly what you just said, which is what happens if your independent variable is multiplied by one of your dependent variable terms. So actually, let's do that one next. Yeah, let's go for it. Let's do that one next. And then based on time, we'll do the other examples I've got prepped up. And if we don't have time, what I'll do is I'll just post a bunch of these worked differential equations for you guys up on Canvas. And then you can go through and look at a bunch of different examples. Okay? They actually do have several more examples that are fully worked ones of these guys. Enough for probably a whole extra day if we had time for it, which we don't. Okay? So let's do an example that meets with what you just asked. So this example goes as follows. So it's t times second derivative of y. So it went back to a second derivative minus t times the first derivative of y plus y equals 2. So notice here the non-homogeneous part is actually really, really nice. It's just a constant. But this guy here is something that you couldn't be handled by the method of undetermined coefficients because it's got the t's here. It doesn't have constant coefficients. Now, variation of parameters could totally handle this guy, except I would have to tell you what the homogeneous solutions were because we haven't talked about, or we didn't go over how you get homogeneous solutions if you don't have constant coefficients. Hint, characteristic equation isn't the thing that you deal with. Well, you don't only deal with that. Okay? So instead, if you have a independent variable multiplied by one of your dependent variable terms here, or if you have weird functions that our other methods can't handle, that's when we're going to have to use Laplace transforms. Now, with Laplace transforms, you typically need to have your initial conditions. So let's have y of 0 be 2 and y prime of 0 be negative 1. So the first step that you want to do is you want to take the Laplace transform. So step 1. Take your Laplace transform of both sides. Now, here's the thing that you have to use. If you have an independent variable involved, you have to use this rule. And the rule goes as follows. It says if you have the Laplace transform of t, and you can actually do this t raised to any power. I'm just going to write down the one that is regular old t because that's the only one we have, just a single copy of t. Well, let's pull back to our rules. We pull back to our rules. I don't think it's in this one. We pull back to our rules. Oops, I was already at the bottom. The one to notice is this guy right here. Oh, that did not work. Here, notice you have t raised to any power whatsoever multiplied by your function is going to equal either plus or minus 1 depending on what that exponent of t is. If t is even, it'll be positive. If t is odd, it'll be negative. And then you take that derivative n times of the Laplace transform of the other function. Now, the one that we're going to use is we're actually going to use this guy right here where you only have a single copy of t. So notice it's the same formula except you only take the derivative of the Laplace transform of f once, and then you negate that derivative. Okay? So that's the key thing that we're going to use. Now let's go back to where we were at. So what we're going to do is, this is the negative derivative of the Laplace transform of, don't write t, of f. Now, for us, what does that mean? This means that if we are looking at the Laplace transform of t times second derivative, this guy would be exactly the negative derivative of whatever the Laplace transform, that was trying to be a Laplace transform, of the second derivative of y is. And then we had forgotten to write the second derivative of y. So let us move this down, and we'll calculate our Laplace transforms just like we did in our previous examples of y, y prime, and the second derivative of y. We might need a little bit more space. So let me move that down just slightly more. All right, just in case. So we have said before that the Laplace transform of y is just going to be our capital Y. Our Laplace transform of y prime was s times y minus our first initial condition. And we'll go ahead and plug that in just a second. And then we're going to have our Laplace transform of our second derivative of y. And this starts off with s squared times capital Y minus s times your first initial condition, and then minus your second initial condition. And we'll go ahead and plug in there as well. So if we start plugging in, we don't do anything for the first one we wrote. The second one we wrote, we'll simply have s times capital Y minus 2. And for our second one down here, we'll have s squared capital Y minus 2s, and then minus negative 1, so plus 1. And it looks like I left us more space, so we'll move this back up. Now, once we have those guys as a background, we can actually do the adjustment factor of dealing with the actual t that we have. So if we look here at t times the second derivative of y, we already know we're going to take the derivative of whatever the Laplace transform of y is, and then take its negative at the beginning. So here we'll have negative, then a derivative. What we'll plug in is s squared capital Y minus 2s plus 1. Yeah. So now we just need to do that derivative. We still have the negative out front. If you want, you could actually pull the negative in right now. But I left the negative out front. If we take the derivative, notice with this guy right here, this first term, we have an s squared times y. S squared is a function of s. Capital Y is a function of s, so you're going to have to use product rule. So we have product rule says derivative of the first, 2s, times the original second, the capital Y, plus the original first, times the derivative of the second. And that takes care of the first term. Second term, negative 2s, the derivative is negative 2, and the derivative of the plus 1 at the end right here, well, it goes away at 0. So if we clean this guy up, this would be negative s squared derivative of capital Y minus 2s capital Y. I just flip-flopped the first two terms, and then plus 2. Notice I also flipped the signs on all the terms. Now that one's the hardest of the two. T times y prime is going to be easier. So here, if we have t times y prime, same rule, negative derivative of the Laplace transform of y prime. So when we grab our y prime Laplace transform that we already calculated from right up here, that's going to be s times capital Y minus 2. So now we take a derivative. The derivative, again, is going to incorporate a product rule. It will always incorporate a product rule for that first term. So here we'll have negative, and I'll go ahead and put in parentheses the product rule. Derivative of s is 1, so we'll just have capital Y, 1 times capital Y, plus s times the derivative of capital Y. And then when we take the derivative of our negative 2, well, it just completely disappears. So if we go ahead and clean this up, this would be negative s y prime minus capital Y. If you have non-constant coefficients on your dependent variables, the setup for the Laplace transform is a whole lot more. When I say a whole lot more, still not tons and tons, but it is about double. just because you still have to compute the Laplace transforms of the dependent variable terms, but when you have these t's in front of it, you then have to do that adjustment that you're dealing with. Now, putting this all together, so all of this is what normally we would put to the aside. Okay? Putting this all together, we're looking at the Laplace transform of t times second derivative of y minus the Laplace transform of t times the first derivative of y plus the Laplace transform of y, all equals the Laplace transform of 2. Okay? Now, we've already dealt with the initial conditions when we were plugging in right back up here. And in terms of the formulas, the Laplace transform of y is just capital Y. We've actually got everything we need to plug in those two lines. So I'm going to go ahead and make this bigger and scooch it up. All right. So this first guy, when we plug in, will be negative s squared. I'm pulling from right here. Negative s squared, capital Y prime s, minus 2sy plus 2. Then we'll pull this guy and plug in for our Laplace transform of t times y prime. So this would be negative s y prime of s minus capital Y. And then our last term one right here, this is just capital Y of s. And then what feels like the easy part, we have to figure out the Laplace transform of a number. And the Laplace transform of 2 is, I'm assuming you're all thinking in your head, 2 over s. Now, technically speaking, that's it for step 1. We just got everybody into their Laplace transforms. So the next thing that we want to do is we want to go ahead and solve for our Laplace transform of a solution. In other words, we want to solve for that capital Y. And all we need at this point is that very last line, that very last black line at the top of the screen there. So it turns out this is a little bit more complicated than before. Why? Because not only do you have a y, you also have derivatives of y now. Okay? So let's look at these guys strategically. We've got a term with a y prime in it, and then we've got a term with not y prime, just regular old y's. So we're going to group them together normally. So when we start grouping them together, we will have for our y prime terms, we've got negative s squared. The other one is, well, distribute the negative in front, so we subtract the negative s, so that's going to be plus s, and all that will be multiplied by our y prime. Then we've got the term with all of the y's. There's 3 of them. Some of them will add together. So here, the first one is negative 2s. The next one over here is this guy, well, it's just got a negative 1, but there's negative here, so that'll flip signs, and then plus an extra one. So these two will be able to combine because they just have constant coefficients. The first one over here has the negative 2s. So plus 1 plus an additional, these guys will be a plus 2. And lastly, there was one term that just had a constant in it, so we'll move that guy to the other side. So our 2 over s minus 2. Now, here's where things can get a little bit interesting. Before we jump into what we're about to do next, or maybe I should just go ahead and do the bit. The thing that we're going to want is we're going to eventually want to solve for our capital Y. But first we have to deal with this guy, and what we need is we need to have a coefficient out front of just plain old 1. So I'm actually going to do this strategically. You don't have to do it the way that I'm about to do it. But what I'm going to do is I'm going to factor the 2 coefficients on y prime and regular y. And I'm going to do this because they actually look really, really similar. So the first one here, I'm going to claim it looks like we can factor out an s. And if we factor out an s, we could write this guy as s times 1 minus s. Or if you prefer, s times negative s plus 1. Or if you prefer, negative s times s minus 1. I just pulled out the single s. Maybe there's a better way to do it in the future, but for right now, I just pulled out a single s. I promise there's a reason for that. Just a second. Now, for that second coefficient that was underlined in orange, I'm going to pull out a 2. Why? Because when we pull out the 2, we'll also get left with a 1 minus s. And that's why I thought about factoring them right now. And on the far side, one of the things that you almost always do, unless you have a discontinuous function where there's an e in one of the terms, not the other ones, you pretty much always want to add those two guys together. Well, if you add these two numbers together, over here in Scratchwork, 2 is the same as 2s over s. So that fraction will actually turn into something over s. Specifically, it's going to turn into, here's the Scratchwork to the side again, it's going to turn into 2 minus 2s all over s. So those were the two asides. Now, why would I have done that second one as an aside? Because this 2 minus 2s, that's the same thing we had right here, just written in the reversed order. So I'm going to write the top actually in this factored form of 2 times 1 minus s whole thing over s. Now, the reason I did that is so we could then come back and say, hey, every single term has that same factor. We've gotten rid of it. In other words, made our lives a little bit easier. So now we have s times the first derivative plus 2 times the original guy all equals 2 over s. And doesn't that look so much easier to deal with? Now, anybody spot what type of equation this is? This is probably the most important thing to recognize with these type of problems. Anybody spot what type of equation we've built ourselves? Got it. It turns out when you have a constant, a non-constant coefficient, so one of your independent variables is being multiplied by your y or your y prime, or in our case, also y double prime, what you actually get here is instead of being able to solve for y where you just factor things like out, like all of our other examples, you actually build yourself a linear or separable in some cases, but a linear differential equation. Which means this is where we have to remember the stuff from solving linear differential equations. What is it that we need to do? We're going to divide out by our leading coefficient. That will be the first step. So if we divide by s in all of our terms, we'll get the derivative all by itself. We'll get 2 over s on that next one. And on the last one, we'll get 2 over s squared. We just divided by s on every single term. Now, for a linear differential equation, we had our integrating factor. And our integrating factor was always e raised to the integral of p of, in this case, s ds. You just put whatever your independent variable is. Anybody spot what that p function is in our current situation? Who would be p right now? Got it? It would totally be this 2 over s guy. So anybody got what the antiderivative of 2 over s is? Yep. So it would be 2 natural log of s. And when you cancel things, this guy, to just remind us of what we've done in the past, 2 natural log of s is the same as natural log of s squared. So this cancels into simply s squared. This now is the time when you multiply the entire differential equation by s squared. So we have s squared, first derivative, plus, well, if you multiply s squared by 2 over s, the s's will cancel, and you'll simply get 2s times capital Y. And on the far side, if you multiply the 2 over s squared by s squared, well, you just get the 2. And remember, in linear, guys, that first bit, which was attempting to be a beautiful bracket and utterly failed, that first bit will always turn out to be the derivative of your function. So that's your capital Y in this case, times your integrating factor. And in the past when we did this, we always checked it. I'm just going to give it to you this time. And it still equals 2. So anybody remember what you did at this stage or what we would do at this next stage? Yep, integrate both sides. You guys are perfectly right. So if we integrate both sides, that derivative will disappear. So we'll have s squared times regular old y equals whatever the integral of 2 is. Don't overthink it. What's the antiderivative of 2? You got it, 2s. And remember, there is always a plus c with linear, guys. This is about to get interesting. So if we solve now for our capital Y of s, what would it have to be? Or how would we get it? So either what the actual answer is or how we would get it, either way. Whichever is easier for you guys to type. So what do you guys think? How would we get to that capital Y? Yep, just divide by s squared. Don't overthink it. So when we divide by s squared, when we divide 2s by s squared, the s and the s squared are going to cancel and give you simply 2 over s. And for this guy here with a c, it's just going to be c over s squared. Now remember, s here is the variable in your Laplace transform. The c is still just some constant that came out of that integral. Now, our step 2 was find the capital Y equaled. We just found that. Now, did we find it in a way that was the same as before? Absolutely not. Here, what did we do? We totally recognized that that guy was a linear differential equation, and instead of trying to factor out and algebraically solve for capital Y, we said, hey, this is a different type of equation. It actually is a differential equation, and we had to go ahead and solve it by way of a linear differential equation. Now, nice factor is, notice this answer right here. That answer of what our capital Y is, or the Laplace transform of our solution, is the original differential equation we had, is actually in a super nice format. Its format is actually way more nicer than our other examples that we had. But you had to do more differential equations work to get here. Okay? Much less algebra work, though. So last step, step 3, is we want to find or recover our original solution, and that's going to be where you take the inverse Laplace transform of whatever answer we just got. So here's what the guy is. We have y equals the inverse Laplace transform of 2 over s plus c over s squared. Now, what do you guys think? What is the inverse Laplace transform of 2 over s? Anybody got a guess for that one? Yes, perfect. So for this one here, the inverse Laplace transform of, actually, let me do a little bit of scratch work here for us. Inverse Laplace transform of the first one is just going to be 2, just going to be the constant. And this guy here is totally what? It's c times the inverse Laplace transform of 1 over s squared. And 1 over s squared was totally, had an inverse Laplace transform of t. So our solution is supposed to be 2 plus c times t. Now, before you think that's the final answer, let us go way back to the beginning of this question. We originally had a second-order differential equation. It had the non-constant coefficients, one of the few times that in this course we're able to handle that. If you have non-constant coefficients, pretty much Laplace transform is your way to go. And if you have these non-constant coefficients, you pretty much are guaranteed that when you take the Laplace transform, you've built yourself a second differential equation you have to solve. Now, it has 2 initial conditions. If you have 2 initial conditions on a second-order differential equation, are you supposed to have a constant in your answer like what we did with our C? supposed to happen if you have two initial conditions and a second order differential equation? You're supposed to be able to have what for your solution? In other words, is an unknown allowed in your solution? What do you guys think? Yes or no? Is that unknown allowed? Correct. It shouldn't be there. You should actually have, we should have been able to go ahead and solve for that constant C. So here's how we do it. And it's going back to those initial conditions. So let me write the initial conditions over here to the side. We were told that y0 was supposed to be 2, and y prime of 0 was supposed to be -1. So that's the stuff that we were given ahead of time. So these guys were given. So let's check to see if they actually work with our solution. So if we plug in t equals 0, we'll have 2 plus c times 0, which is 2. So that first one works right there. No worries. Didn't help you at all with the c, though. Now, if we look at the second initial condition, we're going to have to go ahead and look at our first derivative. And what is our first derivative? Well, the derivative of 2 is 0, and the derivative of c times t is simply c. So what does that tell you about this guy c? Anybody have a guess what that tells you about c? Correct. What it tells you is if your first derivative has to be a constant, and you're already told the first derivative at 0 is -1, well, that tells us that c also has to be -1. Which means, put this all together, we are going to get that the actual answer is 2, plug in the c, minus t. And that guy would be the answer of the original differential equation. So yeah, if you have a t, with Laplace transforms, we're just going to keep it in terms of the variable t all the way through. So if you have a t multiplied by your derivative, or by y, or by y double prime, by any of them, or in our case, by 2 of them, this is where you're going to get, it's typically linear, but it could also be separable differential equation that you would use to solve for the capital Y. Then you should easily be able to solve for the actual solution. Normally it's something relatively straightforward to deal with down here. But sometimes you will get an unknown. Let's face it, you're almost always going to get an unknown because there's a constant of integration that happens. And then that's something that you can take care of either by way of your initial conditions or by some other fact, and where the other fact is dealing with a limit with the Laplace transform definition. But you shouldn't have that second case in our class, and if you do, I would tell you what that other thing is that you need for finding that C. Questions kind of make sense. Could at least follow it when somebody else does it. All right. These guys here with the T's, the example that we had was a non-homogeneous differential equation, but you would still need to use Laplace transforms if this had been homogeneous, so if we had an equal 0. The difference between the homogeneous and the non-homogeneous is often it's a little bit easier to solve the homogeneous one. What you'll sometimes see, especially at this level of a course, and I'm making this example up off the top of my head, something like this. Maybe you've got a second derivative minus 2, first derivative plus ty equals 0, and whatever your initial conditions are. Something like this. This is also a situation where you would need to worry about using the Laplace transforms because of that term right there. This is somebody where you can't use your characteristic equation because you don't have only constant coefficients. But in terms of the workload, it has a tendency to be a little bit shortened when you've got either your initial conditions, like this one over here that's got some zeros in it, or the homogeneous. Still the same basic procedure as that last example. You still have to figure out, hey, what are the Laplace transforms of my first derivative, of my second derivative, and then here, for that highlighted guy, you'd actually use your rule, but it would actually be easier. I'll show you. this would be negative the derivative, first derivative of the Laplace transform of y. But remember, the Laplace transform of y is just the capital Y. This would be negative capital Y with the first derivative. So then, in terms of what you were doing here, your first derivative, that Laplace transform was S, capital S, minus your first initial condition, which is 0. Your Laplace transform of your second derivative is S squared, Y. Maybe I lied. This one might be a little, I didn't pick out anything nice here to make the differential equation look nice. And then here, minus 1. So when you plug in, this guy would be S squared capital Y minus 1 minus 2S capital Y minus your derivative. So this one would turn out to be negative Y plus S squared minus 2S Y equals 1. Or when you clean it up so it's actually linear where everything makes a lot of sense, you do it like this. I just flipped signs, except I missed one of them. Don't forget to actually flip that sign. And I missed the Y. That's a problem too. So here would still be the Y. And then this one would be the thing you'd still have to solve linear-wise. And if you were thinking of checking to see if somebody was actually separable, this would be where you have the equal 0 at the negative 1. If instead of that negative 1 you had an equal 0, then the thing would be separable. And so if you guys prefer separable, you could go that way. Although based off of your guys' test one, most people did a little better on linear, even though it takes more work. Or at least I think it takes more work. It's less algebra. Okay. But that would be sort of the idea behind these guys that deal with the T's. Okay. But that's everything. The other examples I've got prepped up for you guys, I'll go ahead and post them on Canvas under the section of notes and videos. But we're out of time. I'll go ahead and hang out for a little bit if anybody has questions. But that's it for today.